Hi everyone. In this video we are going to cover section 6.5, physical applications, and we get three different applications, application type questions. The first deals with mass and density, and in these mass density problems they all involve finding the mass of a thin rod. And the reason for a thin rod is in order to talk about the mass of something in 3 dimensions, like in the world that we live in, you would need calculus 3 skill sets, and we would need something called triple integrals. You think integrals are fun? Double, triple the fun when we get to triple integrals. So in order to get to that application, we need to be in a different course, but we still give you kind of an introduction to that application and deal with a one-dimensional object. So this thin rod only has length. It doesn't have width or depth. It's one dimension. And we want to find the mass of this rod, and the deal with it is the density is variable. We can represent the density with some function. So maybe as I move to the right of my thin rod, it gets more and more dense as I move further to the right. I'm actually looking at my Apple Pencil that I used to create the notes for this this video, and it's different. It has a different density in different parts of the pencil. It's real thin, but at the cap of the pencil, it's really light. I can actually remove that part, so it's less dense there. At the tip, it's thinner. It's also less dense because there's plastic, and all of the guts of the Apple Pencil, it's more dense in the center where all the computer chips would be. So this pencil has a variable density. All right, and we find the mass of it by, well, as we have done throughout this semester, chopping it up into little pieces and using an integral to add them all up. All right, so here's the formula. It ultimately is the same idea as we've done all along. We have a function, and that is in here in what we're integrating. That's a Greek letter rho. It looks like an italicized p, but it's the variable that we use for density functions. So we integrate our density over the bounds of the integral in terms of x, and that will give us the mass of our one-dimensional object. So let's look at the example. We have a thin rod oriented over the x-axis. Our bounds are from 1 to 3. And the density is given by this equation. So we're given the density function in this one, and we want to find the mass. What it boils down to, let me rewrite the integral formula first. Rho of x dx. We substitute in our bounds, 1 to 3. Our function, 2x squared plus 3 dx. That's it, right? It's another application. The idea being, if I can represent the density with a formula, with an equation, I can find the mass using integration. This is 2x cubed over 3 plus 3x evaluated from 1 to 3. And then when we substitute in our bounds, 3 cubed over 3 plus 3 times 3 is the top bound. 2 times 1 cubed over 3 plus 3 times 1 is the bottom bound. Punch all of that into your calculator, and you should get 23.3 repeating, or 23 and a third, and that would be the mass. We're not given units in this one, but that would be the mass of our object. Our next application is that of work done by a force. And depending on your science classes of the past that you have taken, you may have seen the equation, the formula work is equal to F times D. Work is some force applied over some distance. That's how we compute work. And then in calculus class, what happens when that force is variable, when that force is represented by some function and changes over time? Think about, if you're lifting a chain off the ground, the first link is easier to lift than the second link, than the third link, okay, because you're holding more weight as you lift that chain up one link at a time. Okay, we often look at these examples in terms of springs. So if I have a spring at some x distance, it's at its equilibrium. You can either compress it to shorter than its natural length, or you can extend it beyond its strength. And we also use something called Hooke's law to write our force equations. I'll just put it over here. Hooke's law. Oops. Law. There we go. And it's, F is equal to K times X. Each spring has some constant applied to it, and we're going to solve for that first to represent our force function, and then to find the work done in stretching out that spring or compressing that spring, we are going to evaluate an integral. Our bounds are the distance that spring is moving, or the distance the object is moving, and then we integrate our force function with respect to x. So let's take a look at an example here. And in this one, we're given the fact that it takes 10 newtons in the negative direction to compress a spring 0.2 of a meter from its equilibrium position. How much work is done to stretch it 0.5 meters from its equilibrium? All right, so let's take a look at what this looks like. The first thing is the first step that we'll do is use these two pieces of information to write our force function. So the force, F of x, is K times x for our spring. Technically, because they say 10 newtons in the negative direction, I'm going to substitute negative 10 in for the force, and K stays the same. I'm also going to substitute in negative 0.2 for the distance because we are compressing the spring. Ultimately, we're going to get a positive, right? It would be the same if I plugged in positive 10 and positive 0.2, but using the verbiage from the problem, right, because it's the negative direction and compressing the spring, that's why there's the two negatives there. All right, if you divide both sides by negative 0.2, you get K is equal to 50. So our force function for this spring, F of x, is equal to 50x. And now we're going to stretch it 0.5 meters from its equilibrium and compute the work done to accomplish that task. Integrate from 0 to 0.5 meters our function, 50x, with respect to x. Integrating gives us 25x squared, because 50x squared over 2, evaluated from 0 to 0.5. And then when we substitute in our bound, we get 6.25. And the units for this, so if you don't get the units, I'm not as concerned about the units as I am about the calculus, but we have 6.25 joules of energy. That's the work done to stretch this spring half a meter from its equilibrium. The last problem type that we'll see in this section still deals with work, but now we are pumping water out of a tank. And these problems are a little bit more complicated to set up, so let's go through a couple of scenarios. In this first visual example, we have a water tank that has a radius of 4 meters and a height of 10 meters. Also, we can see that it's filled with 8 meters of water. That's the depth of the current water. And what our goal is to pump all of the water out of the tank. We're pumping all the water out in this example, and we want to know how much work is done. And the reason that our force is variable here is because the amount of work to bring this top layer of water out of the tank is less than the amount of work to bring the bottom layer of water out of the tank, because it has to travel a much greater distance. So the first thing that we can figure out without too much difficulty, I hope, are the bounds for our integral, all right? And the bounds, we can see here, we're setting the top of the tank, because that's where we're pumping the water out of. We're setting that as x equals 0, and x is, the depth as I move downward into the tank. And we can see here that the water starts when our depth from the top of the tank is 2 meters and ends all the way at the bottom of the tank, so our depth would be 10 meters. So the bounds for this problem are from 2 to 10. Now the next level to this is to consider one, cross section, one delta x of water. And I'm going to pause and add on a little picture here. So there's my picture. What that represents is one layer, if you will, of water that is delta X meters thick, really thin layer of water. Okay, but in order to pump that out of the tank, we need to know what its volume is. Okay, so the volume for that piece of water, V equals volume of a thin cylinder here, is pi times the radius squared, 4 squared, times the height of that slice is delta X. V equals, so that would be 16 pi times delta X. Now you can see I just added on another piece of information. We have what's called the weight density of water. So for every, 16 pi times delta X, that would be cubic meters, that's a volume, of water. Its density, the weight density, is this 9,800 newtons per meter cubed. Okay, and if that's a little bit abstract, that's okay. The examples that we go through will be similar to this setup. All right, so those two, we're going to now put those two pieces of information together and say that the force required to lift this water, this thin cylinder of water out of the tank, is 9,800, that weight density of water, times our 16 pi delta X, and that is 156,800 pi delta X. Okay, so I'm going to zoom out a little bit here, and we're kind of at the point where we can put all this together. So where we now want to write our work equation, our work integral, work is equal to the integral, our bounds we discussed a while ago are from 2 to 10, and then our force function that gets substituted into the integral, 156,800 times pi. The delta X, when I plug it into my integral, is the dx. All right, and here's one extra piece that gets included that is not at all obvious, but they give a slightly more detailed explanation in OpenStax. I'm simplifying things a little bit for the purposes of this video, but this X represents the distance that each layer of water travels. Distance each layer of water travels. So when I'm saying maybe 5 meters down into the tank, that slice of water has to get pumped out 5 meters. But when I'm even deeper down here at 8 meters, that water has further to go. So it takes more work to get it out of the tank. Okay, so these problems are involved to set up. So take a look at the other example that's done for you in OpenStax. But let's finish this one off. We factor out the 156,800 pi. Integrate our x, becomes x squared over 2. Plug in the bounds from 2 to 10. Now it's a calculator question, and let's go with the work is approximately 23,000. So I'm rounding to the nearest whole, and I typed pi into my calculator also. 23 million, 644,883, and that would be joules, or 23,650,000 joules of energy to empty this tank. All right, look at the other example in OpenStax. Hopefully that helps you to set up a couple of these. This is probably the most challenging type of problem in the section. Not probably, definitely the most challenging type of problem in this section. So please let me know if you run into any questions and can't figure some out. Thank you very much for listening. We're at the end of the section. Have a wonderful day.